This is problem 8.8.18. It is a 3x3 matrix. We are looking for the eigenvalues and eigenvectors. So of course we know how to find eigenvalues and eigenvectors, so let's go ahead and find the eigenvalues. We know we can find the eigenvalues by finding the characteristic equation from the determinant. So the determinant of the matrix A minus lambda I is 0, and A minus lambda I is going to be 1 minus lambda, 6, 0, 0, 2 minus lambda, 1, 0, 1, 2 minus lambda. And so doing cofactor expansion along the first column, this will be 1 minus lambda times 2 minus lambda, 1, 1, 2 minus lambda, minus 0 plus 0. And that's all 0. Okay, so then we can expand this and get 1 minus lambda times 2 minus lambda times 2 minus lambda minus 1 equals 0. Continuing to expand the right side of that equation, that is 1 minus lambda times lambda squared minus 4 lambda plus 4 minus 1, or lambda squared minus 4 lambda plus 3. That is 0. Okay, and then we should be able to factor this. This is 1 minus lambda times 1, or rather lambda minus 1. Lambda minus 1 times lambda minus 3 equals 0. And so we have one eigenvalue of multiplicity 2. So lambda 1 is 1. And we have that eigenvalue twice. And then we have another eigenvalue. Lambda 2 is 3. So for this 3x3 matrix, we ended up with only 2 eigenvalues. Sometimes we're able to find 2 eigenvectors corresponding to the same eigenvalue, but I believe in this case we will also only have 2 eigenvectors. But let's find out. So we have the eigenvalues, and then, of course, to find the eigenvectors, we construct the augmented matrices A minus lambda I bar 0. So for lambda 1, we will have the augmented matrix 1 minus 1 is 0, 6, 0, 0, 2 minus 1 is 1, 1, 0, 1, 2 minus 1 is 1. Followed by 0, 0, 0. And then it's quite easy to see that if we were to do a sequence of row operations on here, call it R, we could easily obtain the matrix 0, 1, 0, 0, 0, 1, 0, 0, 0. Bar 0, 0, 0. And this sequence of row operations is relatively easy to follow. So then, from here, we see that k1 can be any number, k1, k2 is 0, and k3 is 0. And so our eigenvector, k1, is 1, 0, 0. Because we can choose any number for k1, it's convenient to choose 1. So let's find the next eigenvector. So associated with lambda equals 3, a minus lambda I bar 0, and a minus lambda I will be 1 minus lambda, or 1 minus 3 is negative 2, 6, 0, 0, 2 minus 3 is negative 1, 1, 0, 1, 1 minus 3 is, sorry, 2 minus 3 is negative 1, and then bar 0, 0, 0. So let's see. We can add row 2 plus row 3 and get the new row 3. And that will give us negative 2, 6, 0, 0, negative 1, 1, 0, 0, 0. But that's really all we can do with this matrix. And so from here, we can read off the two equations, negative 2k1 plus 6k2 equals 0, and negative k2 plus k3 equals 0. And then we can just let k3 be any number k3. So if k3 is k3, then k2 is the same as k3, and negative 2k1 plus 6k3 equals 0. So k1 is 3k3. So then from here, we get the eigenvector k2, which is associated with lambda 2, is, if k3 is 1, k3 equals 1, then we get 3, 1, 1 as that eigenvector. So if we summarize everything at the bottom, A is 1, 6, 0, 0, 2, 1, 0, 1, 2. The eigenvalues are lambda 1 equals 1, lambda 2 equals 3, and we only have two eigenvalues, so we could mark this one as of multiplicity 2. And then the eigenvectors are k1 is 1, 0, 0, and k2 is 3, 1, 1. Those are the eigenvalues and eigenvectors of this 3 by 3 matrix.